This is my fourth lecture in the series of Digital Signal Processing Made Easy. Sorry for some delay in the uploading this lecture because of some COVID issues in my family. Now, in this lecture, I will explain about the discrete Fourier transform. I will start with in general, the Fourier analysis, then focus on the discrete Fourier transform. Now, what is Fourier analysis? It's a very important and very well known terms in that Fourier transform, Fourier series and all that. So, in very brief, the Fourier analysis is a mathematical technique that decomposes signal into the sinusoids. As I have discussed in the previous lectures about the decomposition. We have discussed the decomposition of a signal into the impulses. That makes analysis of that very easy. Similar to that, decomposing a signal into the impulses. In Fourier analysis, the signal is decomposed into the sinusoids. That is the sine waves and the cosine waves. Signals. Now, suppose this is your signal. This is, as you can see, this is a discrete signal. It is decomposed into the cosine waves and the sine wave. Here you can see it's a straight line, that is frequency 0. Here is one pulse, here is the frequency is 1. There are two pulses, it has a frequency of 2. Similarly, it keeps on increasing. Similarly for the sine wave. Here you have one wave, here you have two waves, here you have 3, 4 and so on. The signal to be analyzed is decomposed into these cosine and the sine waves. Then these can be combined to synthesize that signal again. So there are two ways. One is decomposition, breaking this signal into the sinusoids, then putting all that sinusoids together to synthesize the original signal. That is your Fourier analysis is all about. Now, why Fourier analysis? What is the importance of Fourier analysis? Why we are decomposing a signal into the sine waves and the cosine waves, into the sine signals and the cosine ones? Aim of the decomposition is to make the processing easier than with the original signal. That we have discussed at length in our previous lectures, that we decompose the signals to make the processing easy. The processing of the original signals may be complex, may be difficult. We decompose into some other signals, do the processing that is easier. Similarly is the case with the Fourier analysis. Sinusoidal signals are simpler than the original signal because of their property of sinusoidal fidelity. Sinusoidal fidelity. What is sinusoidal fidelity? That's a very important property of the sinusoid. Now, sinusoidal fidelity, if the input to a linear system is a sinusoidal wave, the output will also be sinusoidal. It will not be triangular, it will not be square, any something like that. You give a sine wave, you get the sine wave to a LTA system, which is having the same frequency as the original signal. So frequency will not be changed. What will be changed? There will be change, there can be a change, there may be a change in the amplitude or the phase of the original sine wave, with the frequency remaining same and the shape of the wave remaining the same. That is your sinusoidal fidelity. It's only the sinusoidal waves that have this property, fidelity. A square wave, a triangular wave, they do not have any such kind of the properties. So that's why the signals are decomposed into the sinusoidal waves, not into the triangular wave, not into the square wave, anything like that. You can see you give an input as the sinusoidal signal to an LTI system, output you will get a sinusoidal signal. That output will be having the same frequency as that of the input signal, with only change that changes in its amplitude or the change in its phase. So if you want to analyze an LTI system, what we have to study is only change in the amplitude and the phase. In this way, we can analyze the LTI system. Now see, to an LTI system, you give an input as z raised to power n, where z is a complex number, any complex number. Now what you get is output as the same input multiplied by some constant. That may be the change in its amplitude. You give that input, you get the same input multiplied by some constant. That input is known as the eigenfunction. You give some input to a system, you get the same output multiplied by some constant. That input is known as the eigenfunction. That constant is known as the eigenvalue. So here you can see z is a complex number, hz is the change in the amplitude, that is a constant. So system output is system input multiplied by that particular constant. That input is known as the eigenvalue, eigenfunction, and that constant is known as the eigenvalue. It makes the analysis easy. Just you have to know hz or the change in the amplitude to analyze that LTI system. That is the main usefulness of the Fourier analysis. Now, Fourier analysis are of four types. One is for the aperiodic continuous signal. Second is periodic continuous signal. Third is aperiodic discrete signal. Fourth is the periodic discrete signal. It can be explained as that signal can be continuous or it can be discrete. Further, the continuous signal can be periodic or it can be aperiodic. Similarly, discrete signal can be periodic or it can be aperiodic. So we have the four categories of the signal. One is continuous periodic, second is continuous aperiodic, discrete periodic, and discrete aperiodic. Our main focus will be on the discrete signals. These can be computed on the computers only. You can't compute the continuous one. In discrete signals, again it is periodic and aperiodic. Our main focus will be on the periodic signals. Now, what are the names of these Fourier analysis? If you have a continuous and aperiodic signal, this is known as the Fourier transform. If the signal is continuous and periodic, then this is called Fourier series. Similarly, if the signal is discrete and aperiodic, this is known as the discrete time Fourier series. If the signal is discrete and periodic, then we have discrete Fourier transform. Only DFT can be implemented on computers. So, our topic of the discussion in this lecture will be the DFT. Now, this is just brief for all these four signals with their Fourier transform, with their Fourier analysis. In this, you can see the signal is continuous and periodic. The signal is continues, and it is repeating itself. Their Fourier analysis has this equation, and this is its synthesis equation. Now, what you get in the frequency domain in the Fourier analysis, the output as discrete and aperiodic. This is discrete values, and these are aperiodic, are not repeating itself. So if you have continuous and periodic signal, the Fourier analysis, Fourier transform, what you get is discrete and aperiodic. Second is continuous and aperiodic. It's not repeating itself. It's not periodic, but it is continuous. Its analysis equation is this one. Its synthesis equation is this one. Now what you get as output is also the continuous and aperiodic. You have continuous and periodic signal, you get the discrete and aperiodic Fourier. You have continuous and aperiodic, what you get is continuous and aperiodic. Now coming to the discrete signals, this signal is obviously discrete and periodic. It's repeating itself. This is its analysis equation. Now, in frequency domain, what you get is discrete and periodic. If your input signal is discrete and it's repeating itself, it's repeating itself. What the output you get is discrete and periodic, also repeating itself, and the discrete in nature. Now, in this you see the signal is discrete and is not repeating itself. What you get is output as the continuous and periodic. Even if the input signal is discrete but aperiodic, the output you got is continuous. So it cannot be implemented on the computer. Here you have the input that is discrete and periodic. The output you will get is also discrete and periodic. Only DFT can be implemented on the computer. So our discussion of the topic will be DFT. That is discrete Fourier transform, in which the signals will be discrete and the periodic. So basically what it does is discrete Fourier transform changes an n-point input signal into 2-point output signals. I will explain how. These two output signals contains the amplitudes of the components of the sine and cosine waves. As I have explained you earlier, the Fourier analysis changes a signal into the sine waves and the cosine waves. So DFT will change that signals into the sine and cosine waves. What are their amplitudes will be the DFT of that signal. Now suppose this is signal having how many samples? N number of samples. It will be broken into 0 to n by 2 discrete samples. That is called the real part of the DFT. Real part of the DFT contains the cosine wave amplitudes. Similarly, the second is called the imaginary part of the DFT. Again, it contains how many samples? 0 to n by 2. The combination of these two is known as X, K, sometimes denoted like that. So see here, suppose we have 64 samples. Here it will be 64 divided by 2, that is 32. How many samples total are there? 33. Similarly 33 in this. 33 plus 33 we will be having 66, although the input sample is 64. Now this is your time domain signal. It is decomposed into the two. One is the real part that is containing the amplitudes of the sine waves. This is your imaginary part that contains the amplitudes of the sine wave. Now, next, as I've told you, the signal is broken into the sine and the cosine waves. So the DFT basis function is, one is cosine, another is the sine. Cos 2 pi k I upon n is the number of the samples. As in previous slide I have discussed, let it be the 64. It can be 4, 8. Generally it is 2 raised to power something for the easy storage in the computers. Okay, this is the sine wave. First, the value of the k is equal to 0. In this k is equals to 0. Then we will take k as 1. Then we will take k as 2. And so on. 0, it's a straight line for the cosine. Suppose k is equals to 2. Then we will have 2 cycles. If k is equals to 10, then it will have the 10 cycles. If k is equals to 16, there will be the 16 cycles. Similarly, this is true for the sine waves. K is equal to 0, this is a straight line, 0 frequency. 2, it is the 2 cycles. 10, it will be having the 10 cycles. If it is 16, it will be having the 16 cycles. As we have seen in earlier lectures, the discrete signals repeat itself after every n number of samples. So k will be finite in nature. Similarly, this k is finite. So these are finite, that's why they can be stored on the computers. These can be implemented on the computers. Okay. Now these are the basis function. We haven't come to the actual DFT equation for the analysis or the synthesis. So far what we are discussing, the sine waves and the cosine waves into which the signal has to be decomposed. Now we come to the analysis equation. That signal that has to be analyzed is multiplied by that cosine and summed up over all the points of that. Point to point multiplication, then all points are summed up to get one value, one amplitude. Similarly, in the imaginary part, you multiply it by the sine, point to point. That signal is multiplied by that particular sine wave and summed up from all the points 0 to n minus 1. This is for a particular value of the k. You change k from 0, 1, 2, 3 up to n. Similarly 0, 1, 2, 3 up to n. Suppose this is your signal that has to be analyzed. S3, that is your basis function. S3, it will be having the 3 cycles. Then these two are multiplied. You can see corresponding points. 0 is multiplied by 0, first sample multiplied by some first sample, second by first sample, what you get is something like that. Then you add up all that points to get the value of the DFT at particular frequency. Which frequency in this case? K is equals to 3. Similarly, suppose this is another signal. You can't see what is the frequency components it has. In this you can see the frequency components. So for its analysis, suppose it is multiplied by S3. S3 means K is equals to 3 cycles. Both are multiplied. You got something like that. You summed up all these points to get the amplitude at K is equals to 3. Which amplitude? Imaginary one, because this is for the sine waves. This is the way to synthesize. Synthesize means now you know the DFT at all the points and you want to reconstruct the signal. Here you multiply this with the corresponding cosine, this with the corresponding sine, and add up all that to get the one point of the input signal. Then you take the second point 2, let it be, you change I over here, again do the summation, find the second point, and so on. You have the real part, you have the imaginary part, you combine to get the time domain signal. Now see, all things that we have discussed so far was the conceptual thing. What is DFT and how it is calculated? Basically, DFT is based on the correlation. There is more correlation between a signal and a particular frequency that it is multiplied with, you get a higher amplitude. If that correlation is less, you will get a low value of that amplitude. Higher the amplitude, more is the similarity, means that signal contains that particular frequency. Suppose here it is xn, it is multiplied by k is equal to 3, a particular frequency. If xn contains that frequency at k is equals to 3, you multiply these two, summed up all the points, you will get a large value of this constant. This means this signal xn contains a frequency k is equals to 3. Now you take, let it be k is equal to 7. If that particular frequency xn is not containing, the amplitude that you get will be small. This means xn does not contain the frequency k is equal to 7. Now, how to compute this? You have this equation, basic equation, you have signal xn multiplied by e raised to power minus j 2 pi k n upon n. K is equal to 0, you have a particular signal. When k is equals to n, again you will get the same signal. It will repeat itself. So we take the value of the k from 0 to n minus 1 only. Similarly, you got this point. Now these are multiplied by corresponding sinusoids and sum up divided by n, you got the xn. Okay, I will take one example to make this computation clear. Numerical example. Now see here, you have a signal, suppose 2, 1, 2, 1. The value of the x0 is 2, x1 as 1, x2 as 2, x3 as 1. Now you take this equation. What is the value of the capital N in this is 4, because we have the 4 samples in the input sequence. So you put here n is equal to 0 to n minus 1, that is 4 minus 1, that is 3. You put the value of the capital N as 4 over here. You put 4 over here, 4 over here. What we get is n is equal to 0 to 3, and it is minus j 2 pi k n upon 4. This is what you get. Now, it will be, now you put all these values, n is equal to 0, 1, 2 and 3. It is x0 multiplied by this multiplied by 0, e raised to power 0 is 1. What you get is 2. Then you put n is equals to 1, x1. x1 is 1. 1. Here you put n as 1, it will be 2. Over here, what you get is e raised to power minus j pi k upon 2. Now you put n is equals to 2, x2. x2 is 2. You put 2 over here. You put n is equals to 2 over here. 2, 2, 4, 4, 4 is cancelled. What you get is 2 e raised to power minus j pi k. Third is, you put the 3 over here. x3 is equals to 1. Here it is 1. E raised to power minus j 3 pi k upon 2. Now you have to compute these values xk for k is equal to 0, k is equals to 1, k is equals to 2 and k is equals to 3. You put k is equals to 0, put 0 all over here. This is 1, this will be 1, this will be 1. E raised to power 0 is 1. So what you get is 2 plus 1 plus 2 plus 1. That is your 6. x0 is 6. Similarly, when you put 1 over here, you compute the values of sine and cosine for this, sine and cosine this, sine and cosine for this, and add up all these values to get the x1. That will be 0 if you compute it. Similarly, you will get x2 as 2, x3 as 0. This is the way to compute the DFT. What the capital N, you have to take the number of the samples in the input signal. You put the capital N over here, capital N over here. Then you put the values of n is equal to 0 to 3. x0, here it is 0, x1, here it is 1, x2, here it is 2, x3, here it is 3. And add up all these to get this equation. In that equation, you put the values of the k as 0, 1, 2 and 3 to get these values. This is the practical way of computation of the DFT. Now, how to find the DFT? Suppose IDFT, the inverse of the DFT, that is the synthesis of the signal. Suppose you have xk 60, 0, minus 4 and 0. So x0 is equals to 60, x1 as 0, x2 as minus 4, x3 as 0. Now the equation that you have for the IDFT is this: xn 1 upon n, k is equal to 0 to n minus 1, 2k pi n upon n. So n, capital N is 4 in this case, so it will be 1 upon 4. K is equals to 0 to 3. Here it will be divided by 4. Using this equation, we got this thing. Now xn will be 1 upon 4 x0. Then it is x1. Put a 1 over here and put 1 over here. Similarly, x2, 2 over here. x3, 3 over here. Okay. Now put the values of x0. x0 is 60, x1 is 0, x2 is 2, x2 is -4, x3 is 0. You got this equation. In this equation, you have to put the values of n is equal to 0, 1, 2, 3 to get the input signal. You put 0 over here, e raised to power 0 is 1. So this is 60 minus 4. That is your 56. 56 divided by 4 is 14. This is the way to find the x0. Similarly, you can find all other these samples, putting the value of n as 1, n as 2, n as 3. This is a way to compute the DFT. Although DFT and IDFT, the basic procedure is the same. Just you have to use the different equations. One is the analysis equation for finding the DFT, the synthesis equation for finding the IDFT. One very useful property of the convolution is, DFT is to find the convolution using the DFT. How it is found? You have x1n, a signal, its DFT is x1k. Similarly, another signal x2n, its DFT is x2k. You multiply these values of their DFTs to get a xk. Just multiply that to DFTs. DFT of x1n and DFT of x2n. Then take the inverse of that multiplication of these two DFTs, the result of multiplication of these two DFTs. The signal that you got in the time domain will be the convolution of x1 and x2n. So this is one of the methods of finding the convolution. You have two sequences, take the DFT of both, multiply the DFT of these two sequences to get the output, then take the inverse of that. The output that you will get, the inverse of that you will get will be what? The convolution of x1 and x2. So these are the basics. Today what I have explained is the basics of DFT, basics of first Fourier analysis, then DFT, then how to compute the DFT. And in the last I have explained the convolution using the DFT. So this is all about it. Thank you very much.